Okay, so we use real numbers literally every single day, right? But have you ever really stopped to think about the rules that make them all work? In this explainer, we're going to dive into everything from simple addition all the way up to the power of exponents. And you'll see how these basic rules build on each other in some really cool ways.
So let's start with the basics. What happens when you add, subtract, multiply, and divide different kinds of real numbers? Now, you might think you know the answer, but trust me, there are some surprises in store that will totally change how you look at even simple equations. All right, let's kick things off with a big question. You got your rational numbers, the nice, tidy ones like integers and fractions. And then you've got the wild ones, the irrational numbers, like pi or the square root of 2. So what happens when you mix them? Does the answer stay nice and tidy, or does it get a little bit wild too?
Okay, I know this looks a little complicated at first glance, but the secret here is to just treat the square roots, the root 2 and the root 3, like you would treat variables in algebra, like x and y. We just group the like terms together, so all the root 2's get together and all the root 3's get together. Then you just combine them. It's really that simple. And what do we end up with? An irrational number. And that's our first big clue about how these numbers interact.
Okay, so adding irrationals seems to give us another irrational. Makes sense. But what about multiplication? I mean, if we multiply two irrational numbers, we should get another irrational number, right? Well, not so fast. This is where it gets really interesting. And here is the big surprise. Check this out. We multiply the rational parts, the 6 and the 2, and we get 12. Easy. Then we multiply the irrational parts, the square root of 5 times the square root of 5, which, by definition, just gives us 5. So we end up with 12 times 5, which is 60, a perfectly normal rational number. So the lesson here is that sometimes two irrationals can actually make a rational. Pretty cool, huh? So what have we figured out? Well, mixing a rational and an irrational number always gives you an irrational result, no exceptions. But when you combine two irrationals, it's a total wild card. You might get another irrational number, or you might, kind of magically, end up with a perfectly rational one. It all just depends on the specific numbers you're working with. Now that we've seen how square roots can behave, let's build ourselves a toolkit. These are some identities that are going to be your best friend when you're staring down a messy equation. Think of this as your personal square root survival guide. This table basically lays out 6 secret weapons for simplifying expressions. The first 2 show you how to deal with multiplication and division inside that square root symbol. But the third one, oh man, that one's my favorite. It's the difference of squares, and it is a super clever trick to get rid of square roots completely. The rest are just extensions of multiplication rules you probably already know, but they are incredibly handy when you're dealing with these radicals.
So we've been talking a lot about roots, but what about powers? Let's switch gears and jump into the world of exponents, and you'll see that a lot of the same logic we just talked about is going to come right back into play.
Before we get into the really advanced stuff, let's do a quick refresher. You've definitely seen problems like this before, right? What's 17 squared times 17 to the 5th? Or what about 5 squared, all raised to the 7th power? Now, the answers themselves aren't what's important here. It's the rules behind them that we're after.
And here they are, the 4 fundamental laws of exponents. Seriously, think of these as your Swiss Army knife for any exponent problem. The first law tells us to add exponents when we multiply. The second says to multiply exponents when we raise a power to another power. And the third and fourth give us the rules for division and for products. These 4 laws are the bedrock for everything that's about to come next.
Okay, now this is where things get really fun. We've seen how exponents work with whole numbers, but what if the exponent is a fraction? We're about to stretch these laws into some brand new territory. So this might look a little weird. I mean, we all know that 4 squared is 16, but what in the world does it mean to raise 4 to the power of 3 over 2? It sounds super abstract, but it's actually just a really slick way to combine two things we already get, powers and roots.
And here's the secret sauce. For any fractional exponent, like m over n, the bottom number, the denominator n, is the root you take. The top number, the numerator m, is the power you raise it to. That's it. It's just a 2-step process, and it's surprisingly straightforward once you see it. And what's really cool is it doesn't even matter what order you do it in. Let's take our example, 4 to the power of 3 over 2. If we take the root first, the square root of 4 is 2. And then 2 cubed is 8. Now, if we do the power first, 4 cubed is 64,
and the square root of 64 is also 8. See? It's like a mathematical magic trick. Two totally different paths that lead to the exact same answer.
So, what is the big takeaway from all this? It means our 4 fundamental laws of exponents aren't just for integers anymore. Nope, they work for any rational exponents you can throw at them, any fraction at all. And this is a huge deal. It means that whether you're working with 2 squared or 2 to the power of 1/2, the same simple, elegant rules always apply. And that leads us to one final, kind of mind-bending question. We've pushed these laws from whole numbers to cover all rational numbers. So, what's next? Can you even raise a number to an irrational power, like 2 to the power of pi? And if you can, do you think these same beautiful, simple laws still hold up? Now that is something to think about.